Should be waiting for you to introduce me.
Jesse will introduce you.
Yeah. Jesse.
Yeah, no.
It's up on the computer.
All right, welcome back. We're going to go ahead and get started with our afternoon session. Our first speaker is Dr. Jeremy Owens from the Department of Earth, yes, geology specifically,
yes.
Right? I was going to say geology, but I knew. Okay, so yes, welcome, Jeremy.
Thanks for everybody for showing up. Thanks for having me. It's going to be pretty hard to follow up the last keynote lecture. That was fantastic. But we're going to sort of stay with obviously the same theme of oceans, or water, I should say specifically. Here we're going to move on to oceans. But in the same theme, we're going to talk about history, but a little bit older history, right? Without humans, we don't have quite as good of records, so we get to use some proxies, and we'll talk about that. So the title being Deciphering Ancient Climate Change to Better Understand Future Effects on Our Oceans. And so some of this has been some recent research that we've just recently published from undergrads and grad students and postdocs. And so there's some new things, and we're sort of cutting new edges and research to better understand these links. And I'll say my background is actually in environmental science in terms of understanding water chemistry and water resources. And so this is a really, really interesting place to be able to present this work. I moved on to geology because I wanted to understand how climate change is really different in the past from today. And so that's really what drives my research still, is looking at understanding major climate events in the past and trying to relate and understand how they might be affecting our future and what those relationships might be. And so here, everybody's probably seen the Keeling curve. I'm going to show this again here in the next slide. So modern climate change and CO2, and this is a couple artist reconstructions of the Mesozoic, so when dinosaurs were around. You can see a bolide impact sort of in the background and major climate change that's been affected. And then here on the right is actually a rendition of early Earth's history about 4 billion years ago, where the oceans would be very different. CO2 was really high, but had major climate change and evolution, and trying to understand how our oceans have changed and what the oxygen contents might be is really important to understanding what might happen in our future. So most of us have seen this curve, the Keeling curve from the 1960s, where we've been measuring CO2 concentrations for quite a long time, in the last 50 years. And we see this steady rise and increase in CO2 concentrations, and largely driven by anthropogenic release of CO2, and we'll talk more about that. And so this is a large amount of what we understand and have direct observations, but we can reconstruct some of these things in the ancient ocean. And so this is dramatically changing, and I'll show here in the next slide. For glacial, interglacial CO2, as for the last, you can take this back to about 1 million years, and we've stayed between about 280 and about 180 ppm CO2 in our atmosphere. But now you can see that this is sort of the line going up off of it. And today we're at about 407 ppm. We're increasing by about 3 to 3.5 ppm every year right now, which keeps that sort of hockey stick from that last curve going up and rising exponentially. And so CO2 is really important. It's a relatively minor constituent in our atmosphere, but it has direct implications for temperature and a few other things that I'll show. And so if you reconstruct the temperature on the same figure, you can see that there's generally these CO2 and temperature are directly related to each other. There's some variations within this, and that's your system, as it turns out, is kind of complicated. And there's some things that might be overprinting it in some other times, but generally the CO2 concentration in the atmosphere and temperature are directly related to each other. And these are relatively, depends on how you want to look at it, relatively small changes, but they have big implications in terms of how much temperature variation they might be. And so these periods where you have really low CO2 concentrations and low temperatures, you have much greater extent of ice sheets in our polar regions. And generally temperatures are lower. And so when we get these high periods, we have much less glaciation. And obviously as we're climbing this ladder pretty quickly, we're seeing a major decrease in glaciations. And so we've known about CO2 for quite a significant amount of time in terms of physical implications. And so really what we're trying to understand is how this might relate to testable hypotheses that we might see in the ancient record and what this might hold for our future, right? That's really what is important in terms of our research, is really trying to understand how these ancient climate events might impact our future. And so things that you can test and really see is when you have increased CO2, these things should impact temperature, which we've seen temperature rise today and have seen it in the last 150 years, and pretty dramatic increases. But we also can see sea level change, sea level rise from both the expansion of warmer waters. When warm water heats up, it takes up more space, but also through glaciers on land, right, that are becoming increasing the sea level within our oceans. And these are things that we've known for a while. But one thing that doesn't get talked about very much is oxygen contents in our oceans should also change. And that's because dissolved gases warm waters don't hold as many dissolved gases. And so oxygen contents can be decreased. But there's also other links that I'll show here in a second. Other things which I don't have time to go into in this talk is carbon isotopes actually change because, especially with modern anthropogenic CO2, we're releasing very light carbon. And so there's testable and predictable ways that carbon isotopes might change. And one thing that's really being sort of a hot topic is increased ocean acidity. And so the ocean becoming more acidic and being very difficult for things that secrete carbonate shells, such as coral reefs, which is something that we're very interested in. They actually have a harder time. So one thing to really press in this talk is that today this is us, anthropogenic CO2, releasing lots of this CO2 into the atmosphere. And that's happening at unprecedented rates. But what we really equate this to in the geologic record, and we don't really care what the source is, but we can talk about lips or volcanism. So I might use lips, large igneous provinces. But volcanism is a really important aspect, and that's where we can really draw sort of these parallels between the amount of CO2 that's released out of the atmosphere and what that might do to the oxygen contents. And so that's really what I'm going to get into here for the rest of the talk. So how these two are actually really directly related. They're actually intimately linked between each other. And you can see on this equation here at the top. And so we know this from photosynthesis and respiration. Photosynthesis is happening in this direction, so there should be some sunlight, but that takes up CO2 and water, makes organic matter, and releases oxygen, right? Those are the byproduct of photosynthesis. And respiration just happening in the reverse direction, which you and I do on a regular basis. So we take in oxygen and release CO2. One thing to take into account is combustion is the exact same thing as respiration, right? So when we burn fossil fuels, we're driving our cars, we take organic matter, which is the fossil fuels, take oxygen out of the atmosphere, and we actually burn it, and we release CO2. And this is why these things should be directly related. So this is the same peeling curve, but this only goes until about 1990, or starts at 1990. And so this is that increase that we've seen in the first slide that I showed. But the other thing you would expect is if CO2 is increasing because you're burning fossil fuels, you expect oxygen to actually decrease. It's a really, really hard measurement to do, so we haven't been doing it for very long, and it's actually ratioed in the, I just simplified this to show oxygen. But the difference is CO2 is really low in our abundance in our atmosphere, so it's relatively easy to actually measure, where atmospheric oxygen is about 21%. So it's a really small difference. It's tiny compared to the amount of oxygen, but it is decreasing ever so slightly, and it's about the exact same amount as we're increasing CO2. So it's exactly what you'd expect if you're going and using this process through combustion. And so we actually know oxygen is decreasing in our atmosphere. One thing to note, don't walk away from here thinking that we're all going to die because we don't have enough oxygen, right? We have plenty of oxygen. It's still at 20%. It's not going to harm animals in that sense, but it is decreasing and doing what we'd expect on a sort of chemical level. So for this, we're actually really interested in what does this mean for waters? And so we're going to relate this to the ocean. And really what's important is we're actually seeing surface ocean deoxygenation. And we're seeing this at a pretty rapid rate. And so this figure is showing here in red is the places that are decreasing in the amount of oxygen over a decade. And on blue is places that are actually slightly increasing the amount of oxygen over that same given time. And so in the last 50 years, we've actually decreased our surface oxygen content in our oceans by about 2%. And the prediction in the next 50 years is it's going to be somewhere between another 1% or maybe even up as much as 4%, depending on different model predictions. And we don't have a really long record of this, but this is really interesting and tells us, hey, these processes that we're doing from CO2 release and atmospheric temperature increases, which leads to surface ocean increases in terms of temperature, then decreases our oxygen. And so it's sort of a cascade of events. So why is that really important? Well, oxygen is obviously incredibly important for living things in our oceans, right? So all those respirers that need oxygen. And so one of the things that we're really interested in, how does this affect the marine ecology and the biogeochemistry of the ocean? So the modern ocean is highly dynamic. There's places that have more oxygen than others. And so there's places in the ocean that we call oxygen minimum zones, or OMZs, which is what this is. And so at 200 meters water depth, you can see the places in blue or purple have less oxygen in the oceans. Places in red are very well oxygenated. But these, it's highly dynamic and it's different in various places. And this is things that we can predict from upwelling, cold, nutrient-rich waters that then fuel primary production and then consumption, so respiration. And so this sort of naturally has happened and has happened probably throughout Earth's history. But what we're actually seeing now is that these are becoming more expansive, and not only are they just oxygen minimum zones, but they could have completely devoid of oxygen in these regions, right? So that's where it becomes really important. And if you take this another step and you lose all the oxygen, but eventually you might actually accumulate sulfide or sulfidic conditions in your ocean. And sulfide is that rotten egg smell you might smell if you go to Yellowstone. Well, it's incredibly toxic to most organisms. And so this could lead to extinction events. And these are the things that we're really interested in. If we keep pushing this system, will we, I should say. We don't really want to be, but will we push these systems into more toxic sort of regimes within our ocean? And so I'm going to skip here, and we're going to go through our history. It's relatively short. It's only 4.6 billion years. So if you look at sort of why this matters in terms of the oxygen in our oceans and atmospheres through time, you can really sort of pick out sort of why we're interested in this. But here's the start of Earth, roughly about 4.6 billion years ago. You can see oxygen is incredibly low. This is the oxygen content here in the atmosphere. So this is about many orders of magnitude lower than today. Today is about 21%. It's incredibly low for almost half of our Earth's history. So about 50% of Earth's history, we have almost no oxygen in our atmosphere. And finally, at about 2.4 billion years ago, we accumulate a little bit of oxygen. And that's why we think that these things called cyanobacteria are photosynthesizers that produce oxygen, called oxygenic photosynthesizers. they start actually really becoming abundant and help increase the amount of oxygen in our atmosphere. And then we go another, what's considered in geology the boring billion, about another billion years where we have relatively low oxygen and quite possibly even lower than what this is predicting. Before we had this really big bump in oxygen concentrations at about 600 million years ago. And this is not coincidentally, this is when you see animals actually become evolve and that you can actually see them in the geologic record. And that's because there's enough oxygen to actually support these large animals and they're really oxygen needing sort of organisms. And so that's at about 12, or there's about 12% of Earth's history left, or about 88% of Earth's history has already passed by the time we have animals that evolve on our planet. And then things that we really think about, and I'll actually focus on time periods between the appearance of dinosaurs and the extinction for this talk. But the appearance of dinosaurs happened about 95% of Earth's history. And they lived for quite a long time, but they go extinct at about 98.5% of Earth's history. So they're alive for about 4% of Earth's history, right? Which is several hundred million years that they lived, but it goes extinct over that time. And humans appear sort of at the very last blink of an eye, which is 99.9. If you have many more orders of magnitude, you put it out there for 90%. And so the interesting thing that we're doing, right, is we're directly affecting CO2 concentration in our atmosphere in a really, really quick and short amount of time. And that's really the aspect that we don't fully understand because we don't have a geologic record that probably goes through that quickly. All right, so we have to assemble the climate record. This is an incredibly complicated puzzle, but we're trying to put different pieces to the puzzle. And so we can do this by using proxies, just like we do for tracking a killer with DNA or fingerprints. We can do that through the geologic record. And so we can do this with ice cores to do something for CO2, but I'll talk very briefly about geochemistry to assemble this puzzle. And so to do this, we can use various things like instrumental records, which don't go back very far, about 100 years. Things like a historical record, which is anecdotal evidence of individual people's experiences. Tree rings, which are quite good, but don't go back very far because trees don't exist for that long. Ice cores, which go back until we have no more glaciations. Coral reefs, which can be much broader, but we generally use for these deep time is use ocean sediments. And they can provide a lot of interesting information, but they're also can be difficult to decipher. So here's some sediments core, and this is where the dinosaurs go extinct. That's the iridium spike that many of you might have heard of. And so we can also do things like look at the sediments that might be in a Yellowstone hydrothermal pond to understand what the environment was. So how does this relate to what we're interested in? This is a quick record here of ocean production. So this is sort of, you can think of it as volcanism here. So you can see when these are high, you have relatively high CO2 concentrations. This is relative to today. But you also have really warm temperatures, major high sea level. So these are all sort of related and linked together. But importantly, I'm going to look at these orange bars are sort of extinction events as well. And during these times, you have major oil production. And it's interesting that these major climate events bury lots of oil, and that's what we're actually using today, which is probably causing major climate change. So you can look at, we call them oceanic anoxic events. And these are time periods where we think there's high volcanism. And that high volcanism increases CO2, likely also increases nutrients to the ocean, driving primary production. And indirectly, it enhances weathering, which also increases nutrient fluxes, increases temperature, which drives that low solubility of oxygen in the oceans, and also changes ocean circulation. So these sort of are natural environments to understanding our current and possibly future climate change. So we do this through chemistry, and I'm not going to go through all this. I'm going to show one slide on data, only because it's good as a scientist to actually show the data and not just make cartoons, which is generally what the slides are on this. But so what we've done is look at different trace metals, and these are redox sensitive, and so we're understanding something about oxygen contents within this. And so this gray bar here represents the event, but what we're really interested in is that before this event is that we see major changes in various different elements. actually before the event, at about 50,000 years before the event, which actually shows that the oceans became more deoxygenated. And the event represents sort of an extinction event. And so we're actually seeing that it becomes more and more deoxygenated before this major climate event that happens, much like what we're probably seeing today. And so you can relate this to the volcanism aspect, is that previous to this event, about 200,000 years, there's volcanism that is happening, maybe probably suppressed, not quite as large, but there's sort of this main kickoff of volcanism that happens right at about 50,000 years, which is simultaneous to the expansion of marine deoxygenation. And so you sort of have this increase in CO2 driving all of the warmer temperatures and deoxygenating the oceans, which then eventually leads to this major climate event and also an extinction. And so this is just one event, but I'll show you one more here in the next slide that we've been looking at as well. And this is incredibly more complicated than what we need to talk about here. But here's the species that are present. And so you see a major drop just before the climate event, which is this dark gray bar. You can see a big drop, and eventually it kind of comes back slowly. And this initial drop here, we actually see the same thing as we see deoxygenation of the oceans prior to the major extinction event. And so this is suggesting that we're sort of priming the system and reduce the amount of oxygen, which will eventually lead to this major extinction event. And I'll point out that there's a big sea surface temperature change as well, which is kind of stepwise simultaneous to this. And this down here is the volcanism, which is low before the event and then sort of creeps up in the middle of it and eventually sort of declines. And so this is supposed to be sort of relating to the analogous of what we're doing in terms of anthropogenic CO2 increases and possibly what could happen to the ocean, the oxygen in our oceans. And so this sort of sets up this cascade of events, and the cartoon is probably a little bit easier to understand, but here on volcanism, as you sort of have a typical baseline with a little bit of an increase, which is probably where we're at today, is this sort of initial increase where you don't really see changes in deoxygenation or anoxia. But eventually it kicks up to being bad enough, which is the same time as we see anoxia. And here on the right is the extinction record. And so things that are really oxygen dependent, such as in this record here, radiolarians, they actually start decreasing well before the event. Other organisms that maybe need a little less oxygen might take a little longer to take that hit of extinction or turnover. And then things like forams, which can change where they grow at or live, they might actually increase in their concentration because there's not as many things competing or taking them, predating them. But eventually, because it gets bad enough, they actually take a hit as well. But really what primes the system is this low oxygen conditions, which is set forth because of CO2 increases, probably by volcanism. And I know I'm getting close to time here, so I'm not going to actually go into this, but what we're doing here at FSU with my group is we're really trying to understand this. And what we're seeing, so if you take this, we're looking at vanadium isotopes, but the modern ocean concentration is about 250 micromolar, so it's way out here. But what we're really interested in is these really low oxygen conditions, which might be really important for organisms to exist. And this is the first time that we really have a proxy that can really tell us about these low oxygen conditions. And so what I'll say with that is stay tuned on sort of what we're finding with that. But it's kind of its initial stage, and we're just starting to look at ancient climate events with some of these new geochemical proxies. So what I wanted to sort of to leave everybody with this talk was, what are some solutions and what can we think about in terms of how to make positive impacts on our oceans, right? These are really important sort of questions. We talk about overfishing our oceans and things like this, but over long term, what happens if we deoxygenate our oceans and have lots of anoxic conditions? And so one of the major things, which is almost impossible for any individual person to be able to change, is decrease carbon emissions, which would be obviously really important for lots of different climate impacts. But what I'll focus more on are things that probably more individuals can do, which is decrease nutrient input into our oceans. And we hear about this a lot here in our region with the springs that we have and having lots of primary production that might happen, causing them to not be so clear. So sort of a two-part edge there that we can help our local springs, but also help the global climate. But reducing excess fertilizers, decreasing our untreated wastewater input, which is incredibly important. And lastly, I think that one of the major things that all of us can do, and we have lots of this here in Florida, is protecting our estuaries and marshlands. These are really, really effective places that are sinks for CO2, so they take up lots of CO2 and actually take up these excess nutrient runoffs that we might have. And so the more we can save these sorts of regions of our, especially in Florida, but in our sort of worldwide, will be really important in sort of helping to at least slow this major climate change down. So lastly, I'll just say thank you, and there's lots of acknowledgments, and this cartoon is one of my favorites in terms of understanding climate change and what we should be doing. So thank you.
All right, we have about 6 or 7 minutes if you remain.
You can come up and change yours. Yeah.
Dr. Owens, you had a slide early on about that at about, I think, 300 feet, you get this anoxic condition in the oceans. And then again at 1,000 feet, it seems to return to normal. Why is that? Yeah, like right there. Or sorry, meters. Wow, yeah. So and then it kind of starts turning back, and then you get to the hadals, and like, why does it kind of normalize as we go deeper?
So this is really productive regions of our ocean. So you can imagine there's lots of primary production.
Okay.
So there's lots of oxygen production.
Yeah.
So there's things that are being respired, and it's at steady state. But after you fall below this, you have lots of respiration, no more photosynthesis. And so you're respiring all that the organic carbon, which uses that oxygen. So that's why you go through this. But here it returns because of ocean circulation. So you have deep water that's renewing from the Arctic regions, but are bringing oxygen-rich waters up, and so it actually brings us up and sort of normalize.
Yeah, could you go to the slide that shows the deoxygenation that you have?
The cartoon. This one?
Towards the front. On what the colors where it was red.
Yes. This one.
That's one. Yes. Okay. So as I'm seeing this, it looks like up in the North Polar area that it's darker and showing more deoxygenation than in other places. Am I reading that?
Yeah. Right. So this is much more.
Right. Okay. So what's the explanation for that in the polar regions, and would you expect that to accelerate as we lose more of the ice cap? In other words, is that something that's connected there that
Yes.
you would expect that to happen more as the ice cap contracts?
Right. So this is relative to the decades previous.
Right. Okay.
So this actually still has a lot more oxygen in it than you might find it here in the equator.
Yeah.
Because it's colder.
Right.
But compared to previous decades, because it is warming, you're actually having less oxygen in those waters. And so as you progress through warming our Arctic's up, you'd expect to have less and less oxygen compared to previous decades up at those regions.
Right. Okay.
Yes.
So would you then expect over time, if it continued to warm and it continued to deoxygenate, then that water, particularly if it's no longer colder and it doesn't sink down as far and then regenerate the oxygen for the other areas that it runs into, right? So how does that connection then influence the rest of these?
Yeah, that's a great question. So as normally this cold, dense water rejuvenates the oxygen for other portions of the ocean. And so that's the important aspect, is that now you have less oxygen in those regions. What I'll say is we don't really know.
Okay.
But we do have some records of more recent sort of glacial, interglacial, that when these things shut down, you actually do see less oxygen. But we're still trying to understand how these changes might affect ocean circulation over relatively short times. The climate change events that I was talking about last 500,000 years, right? So these are long compared to modern, long protracted events.
Yeah.
But these are pieces of the puzzle that we don't have fully put together. People are working on and trying to understand those.
Did you see that article that was published earlier this week about diagenesis occurring in our deep sea cores? And so we may actually be underestimating how cold it was in warm periods by like 15 degrees. Like that just came out this week that our
Yes.
proxies are maybe wrong by as much as 15 to 20 degrees. And so it's maybe actually worse than we think, and our sea surface temperatures may be more catastrophic than we think they are. Did you see that?
I did not see the
I didn't
article.
get to read it yet. It just came out this week. It came across my science alerts feed, and I was like, oh, bookmark it out for later.
Yeah, there's certainly, as we're trying to untangle these records and really decipher what they're telling us, there's lots of processes we have to take into account.
Mhm.
So sometimes, do the best you can. But, I wouldn't be surprised. Certainly, our sea surface temperatures are probably more questionable, but the trends we see are probably correct. So absolute numbers are hard to pin down.
Right.
Any other questions? Thank you.